All right, 2018, Calculus BC, number 6, a power series question. The Maclaurin series for log of natural logarithm of 1 plus x is given by that. On its interval of convergence, this series converges to the natural log of 1 plus x. Great. Let f be the function defined by f of x equals x times the natural logarithm of 1 plus x over 3, which is a bit different than log of 1 plus x. Part A, write the first 4 non-zero terms and the general term for the Maclaurin series for f. All right. So I've written what they gave us up here on the board, carefully avoiding the 2 spots of light that are glaring at you. We have the first 4 non-zero terms of natural log of 1 plus x, followed by ... and then the general term. And it asks us for the first 4 non-zero terms of the Maclaurin series of this guy, followed by the general term. So let's, first of all, instead of starting with f of x, let's start with just the part of it that doesn't have multiplied by x. So log of 1 plus x over 3. So log of 1 plus x over 3 is only different from log of 1 plus x with the x over 3. So wherever there is an x here, I'm going to write x over 3. X over 3 minus the quantity x over 3 squared over 2 plus the quantity x over 3 cubed over 3 minus the quantity x over 3 cubed over 4 plus ... plus the general term now. It's going to be negative 1 to the n plus 1 x over 3 quantity to the n over n. And if I wanted to rewrite that, it would be x over 3 minus, okay, we're going to get x squared over 3 squared, so I can put that 3 squared down here. 3 squared times 2 plus x cubed over 3 cubed times 3 minus x to the 4th over 3 to the 4th times 4 plus ... plus negative 1 to the n x to the n over 3 to the n times n plus ... This should also have a plus ... All right, that's log of 1 plus x over 3. If I want x times the natural log of 1 plus x over 3, I just have to multiply all of this by an extra factor of x. X times this whole thing, which means every power of x is going to be increased by 1. So we're going to have x squared over 3 minus x cubed over 3 squared times 2 plus x to the 4th over 3 cubed times 3 minus x to the 5th over 3 to the 4th times 4 plus ... plus negative 1 to the n x to the n plus 1 over 3 to the n times n plus ... And that's part A for us. Simple manipulation of power series question. Substituting x over 3 in for x, and then multiplying by x, which just multiplies each term by x, shifting the powers 1 higher. Part B. Determine the interval of convergence of the Maclaurin series for f. Show the work that leads to your answer. Okay. From my work in part A, I've copied over just the very last thing I had written down, which was the general term for my function f. So let's go ahead and use the ratio test to find the interval of convergence. So I'm looking for this quantity that we call rho, which is the limit as n goes to infinity of the absolute value of the ratio a n plus 1 over a n. So a n plus 1 is going to be what I get when I plug in n plus 1 for every n. So that's going to be negative 1 to the n plus 1, x to the n plus 2, divided by 3 to the n plus 1 times n plus 1, all over just this exact thing again. Negative 1 to the n, x to the n plus 1 over 3 to the n times n. That's going to be the limit as n goes to infinity of the absolute value of, since this is negative 1 to the n plus 1, negative 1 to the n, and I'm taking the absolute value of all this, those are going to disappear. I don't need to worry about them. So it's just going to be what? Well, on the top there's going to be an x to the n plus 2, and then a 3 to the n and an n when I flip this denominator. So x to the n plus 2 times 3 to the n times n. And in the bottom here, I'm going to have my x to the n plus 1 from that denominator. I'm going to have a 3 to the n plus 1. I'm going to have an n plus 1 from right there. Oh, just had room for it. Great. And so, all right, that's going to be equal lim as n goes to infinity. The limit as n goes to infinity of, all right, all right, okay. X to the n plus 2 over x to the n plus 1 is just, leaves an x to the 1 left over. So that's absolute value of x to the 1 times, and the absolute value of this stuff, since n is positive, this stuff is always positive. 3 to the n over 3 to the n plus 1 is 1/3. N over n plus 1 is, well, n over n plus 1. And 1/3 absolute value of x can come out of the limit. And the limit as n goes to infinity of n over n plus 1 is just 1. So I need my rho to be less than 1 if this thing is going to converge absolutely. So if 1/3 absolute x is less than 1, that implies that the absolute value of x is less than 3. And so that's the radius of convergence is 3. So my series will converge absolutely within its radius of convergence, so on -3 less than x less than 3. To get the interval of convergence, I have to ask for each of these two endpoints, does it converge or not? So now I have to test the endpoints separately. Let me clear some space to do that. All right, I've left this down here, -3 less than x less than 3, and I'm testing the endpoint separately. I'm starting with endpoint x equals 3 and plug it in. I've written for here, from part A again, the expression for f of x, the power series expression in open form. So x equals 3, I get 3 squared over 3 minus 3 cubed over 3 squared plus 3 to the 4th over 3 cubed times 3 minus 3 to the 5th over 3 to the 4th times 4 plus plus -1 to the n, 3 to the n plus 1 over 3 to the n times n plus which simplifies to, okay, 3 squared over 3 is just 3. 3 cubed over 3 squared is 1. 3 to the 4th over 3 cubed is, 3 cubed over 3 squared is times 2 is 3/2, everybody. Whew. Plus 3/3 minus 3/4 plus plus -1 to the n times 3 over n plus And you'll notice that this is just 3 times the harmonic series. Excuse me, it's 3 times the alternating harmonic series. Converges because it is essentially just a constant multiple of the alternating harmonic series. So, I don't have to have a question mark here anymore. This is a less than or equal to. And now let's try the other one, but I have a prediction that it's going to be basically just the harmonic series, right? In fact, let's cheat a little bit. Cheating a little bit, if I plug in -3, it's going to be -3 squared minus -3 cubed plus -3 to the 4th minus -3 to the 5th plus plus -1 to the n times -3 to the n plus 1. Which equals, okay, this is going to be just a positive now, 3 squared over 3. Negative minus a negative is a plus, 3 cubed over 3 squared times 2 So everything is just going to have a plus sign instead of alternating, which means it is not going to be the alternating harmonic series. It's just going to be the regular old harmonic series, or 3 times the regular old harmonic series, which diverges. Classical example of a conditionally convergent series, the alternating harmonic series, and a divergent series, the regular harmonic series. So this is the interval of convergence. A strict less than, because -3 is not included. A less than or equal here, because +3 is included. It's time for part C. Let P4 of x be the 4th degree Taylor polynomial for f about x equals 0. Use the alternating series error bound to find an upper bound for that thing, the absolute value P4 of 2 minus f of 2. Okay, so that little absolute value expression is just saying find an upper bound for the difference between the 4th degree Taylor approximation of f of 2 and the actual value of f of 2. And the alternating series error bound just says if you've got an alternating series, then the error is bounded by the absolute value of whatever the next term in your series is. So if it's a 4th degree polynomial, it'll be the 5th power of x term in the series. Let's write that down. Okay, well, up here I still have f of x, the first several terms. Now P4 of x just means the 4th degree Taylor polynomial. So as soon as I get to x to the 4th, that's when I'm stopping. So it's going to be x squared over 3 minus x cubed over, let's just simplify this, 9 times 2 is 18, plus x to the 4th over 3 times 27 is 81. All right. And then I'm going to write one more. Oh, well, actually, I should stop. That is, period. That is the 4th degree Taylor approximation of P of f of x. Now, by the alternating series error bound, right, P sub the error that you get when you use P sub 4 of 2 to approximate this thing, P sub 4 of 2 minus, is less than or equal to, since it's an alternating series, it's less than or equal to the absolute value of this next term. So, right, f of 2 is what you get when you plug in 2 for x. P sub 4 of 2 is 2 squared minus 2. So the difference between them is at most the absolute value of negative 2 to the 5th over 3 to the 4th times 4. Taking that next term in the series, the x to the 5th power term, and plugging in the number 2, which is what where we're evaluating these at. So that's going to be 2 to the 5th over 81 times 4. What are we supposed to show that it's less than? It just says find an upper bound. Oh, well, okay. I mean, how about 32 over... I mean, we're done, really, right? We don't have to simplify on the AP exam, so that's valid. But, okay, I already started. 324 is an upper bound. And that's all.